space until Calc 3.
Oh, good. Are these line intervals?
Not yet. And that's because in 2 dimensions we have this concept of slope, which makes lines in 2 dimensions very easy to describe, to talk about. But in 3 dimensions, there's no slope is not well defined. Slope is how one variable changes in relation to another variable. Well, in 3 dimensions, we have relationships between several variables. So slope, we can't use the concept of slope to describe lines. But we're going to, in 3 dimensions, we're going to use vectors. So here's our setup. I'm going to draw a coordinate system, our 3-dimensional coordinate system. And here is a line in space. And we're going to have a point on the line. We're going to call that P. And its coordinates are x1, y1, z1. And then we have point Q is just some arbitrary point on the line. And its coordinates are x, y, and z. And this is my line L. So line L goes through points P and Q. What we're going to use to describe a line in space is a vector that is parallel to the line. So I'm going to call that vector V. And this vector V will give components A, B, and C. So what we're saying is L is parallel to vector V. We call V the direction vector for the line. So the direction vector takes the place of the slope, really. The slope in 2 dimensions, our direction vector gives us the direction in 3 dimensions. And we need the three numbers to describe our direction. And we call A, B, and C are the direction numbers. And again, they're the coordinates, or the components of this vector that's parallel to our line. So what we're going to do to come up with an equation, and actually we come up with equations for the line, is we turn this vector from P, or this segment from P to Q, into a vector. So from our point that we know is on the line to some arbitrary point on the line, we're going to define the line as the set of points Q, so some are arbitrary points, such that PQ is parallel to V. So that's how we're going to define a line in three-dimensional space. We have a point that we know is on the line. The line is all the points such that the vector from P that we're given to some arbitrary point is parallel to this vector. Well, if PQ is parallel to V, then PQ is a scalar multiple of V. And we can write that PQ equals TV for some scalar t. So t can be any quantity, any scalar, and that will give us another point on that line. This PQ equals TV is the vector equation for a line in space. So this is our, there it goes.
Out?
Yep, into the math office.
Oh, did the mouse just leave?
Yeah.
He was like,
Very.
Like, yeah, this, he thought vectors were a little too much for the mouse. This would have been pre-calc, he would have been okay.
I'm thinking that too. Is Dylan in this class?
All right.
Couldn't handle the knowledge.
Right. So this is our vector equation. This is you will see this as an equation for a line in space. But we want to work with it in a slightly different form. So we're going to write this out explicitly and come up with a set of parametric equations for a line in space. So we don't have one equation, a linear equation like we do for lines in the plane. We have a vector equation, so we have to work with the components. So we're going to end up with 3 equations. All right, so we're going to say that PQ, well, T, we can think of T as our parameter. So PQ is the vector x minus x1, y minus y1, z minus z1, and that equals T times the vector a comma b comma c. That's what our equation. We're just writing it out in component form. And then we equate components. And we get that x equals, I'm solving for x here, x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct. These are the parametric equations for a line in space. And sometimes you'll hear this set of parametric equations called the standard equations for a line in space. And what we're seeing here is that L contains the points x1, y1, z1, and it's parallel to vector ABC. So our parametric equations give us the point that's on the line, and it gives us the components of the vector that's parallel to the line. And notice that each of these equations is a linear equation. We can eliminate the parameter. So to eliminate the parameter, we solve each equation for t. So each of these equations we can solve for t, well, and t has to be the same. And then we get the symmetric equations of a line in space. X minus x1 over a equals y minus y1 over b. equals z minus z1 over c. These are the symmetric equations of a line in space. And the symmetric equations kind of give us some information about how the pairs of variables are related to each other.
Is this related to Lawson's?
No, it just looks similar. All right, so let's look at a quick example, and then we will talk about one thing that we're going to be interested in a lot is distances. We want to be able to find distances from things in space to other things in space. So we want to find the parametric and symmetric equations for the line through -2, 0, 4. That's parallel to 2, 4, -2. All right, so this gives us our direction numbers, A, B, and C. It's our direction vector. And we can write our parametric equations right away. X equals -2 plus 2t. Y equals 0 plus 4t. And Z equals 4 minus 2t. And if we plug in a value of t, we would get another point on this line. What value of t does this correspond to? T equals 0. So we can, our parametric equations of our line are not necessarily unique. We could parameterize it differently. But in this parameterization, this point that's on our line corresponds to t equals 0. Well, we substitute any value of t, and we get another point that's on the line. Our symmetric equations. So these are our parametric. Symmetric. We just solve each equation for t. So we get x plus 2 over 2 equals y over 4 equals, I'm going to say negative z minus 4 over 2. And those would be our symmetric equations. Usually the parametric equations are going to be the most useful. What if we were asked to find the parametric equations for the line through -3 to -3 and 1, -1, 4? I'm not going to go through all the calculations, but let's talk through the procedure here. What would we have to do? We need to make a vector. So we could call this point P and this point Q. And we would find vector PQ, terminal minus initial. what does that give us? No, not the numbers. Well, what does the vector PQ give us in terms? This will give us our direction vector. This is a vector parallel. That's going to be parallel to the line. That's our ABC, our direction number. And we need a point on the line to write our equations. We could use P or we could use Q. Either one. P or Q can be our point on the line. And if we pick, depending on which one we pick as our point on our line, we'll have a slightly different parameterization, but they will give us the same line. So that would be our process. All right, so are we good on those examples? Yes.
Would you be able to do like a vector to P and then a vector to Q and then do like P minus Q to get the vector like of the line that connects them?
Yeah, you could do that.
But, like,
Yeah.
So it would be parallel. It would be like the exact line. Is that more useful or like no?
As long as your vector, the vector that you choose as your direction vector is parallel to the line, it doesn't matter.
Okay.
So if you can find that parallel vector some way, then you're fine.
So you don't have to, so the little drawing we drew, we put it at the origin, which is
No.
kind of convenient. So if you literally just find vector PQ wherever that may be,
Yeah.
that's the space. That's
As
the
long as
space.
it's parallel to your line, you're good.
And finding vector PQ is always
Yeah.
okay.
Right. All right, so one of the things that is important, one of the things that's important in general is finding distances. So let's talk about how we find the distance between a point and a line.
I think it's senility. I think. I've never heard that. Yeah, it's not. Like you never use it now.
Senility is a word.
Yeah, I know. Never use that.
All right, so what we're interested in here is, here's my line. And here's, I'm going to move this down a little bit. Here's my line. And here's a point. I'm going to call that point Q. And we have a point on the line P. What we're interested in is this distance. So we have a line in space, we have a point in space, and we're interested in the distance from the line to the point. Well, here's what we're going to do. You might guess that this has to do with vectors.
Yes.
We're going to draw or make vector PQ. And we also, since this is a line in space, I'm going to say that we have this vector v here. V is parallel to the line. And we're interested in this distance. Well, here is the angle between V and vector PQ. Well, this distance, based on this triangle, this hypotenuse, is the magnitude of PQ. So this is the magnitude of PQ times sine theta. What is that related to that we've been talking about? A cross product.
Projection.
We know that the magnitude of PQ cross V equals the magnitude of PQ times the magnitude of V times the sine of theta. So this quantity, PQ sine theta, is, so our distance is the magnitude of PQ cross V over the magnitude of V. So we find the distance between the point and the line using a cross product. So what we do is we choose a point on the line, make the vector from that point to the point we're interested in. So we make vector PQ. We know the direction vector for our line. So our distance is going to be PQ. Cross that direction vector, take the magnitude, and divide it by the magnitude of our direction vector. So cross product is going to give us a distance. So that's kind of an interesting idea, though, right? That a cross product is going to give us a distance. No, the area of the parallelogram rule is going to be very useful in chapter 15.
Oh, Jesus.
So we're going to integrate a cross product to get a surface area.
Oh, Jesus.
All right. I just want to do one example that involves this idea of a distance between a point and a line. And what I always recommend is you can memorize a formula, you can write down the formula, but if you think about the geometry of it, you'll be much better off. If you think about this little triangle, that's where that formula comes from. It's not just a magical formula that you write down and forget about. It comes from a right triangle.
So the other stuff that you're talking about is the very important number in 3D space, whereas this is something we can kind of flatten and look at like this.
Right, well, because a line and a point are always going to form a plane. So we can use that, yeah, we can flatten it. All right, so let's look at an example. Find the distance from 115 to the line given by x equals 1 plus t, y equals 3 minus t, and z equals 2t. So we need a couple of things. We need a point on the line, and we need the direction vector for the line. So we need the point on the line to make our vector PQ, from P to this point Q. Well, what's a point on the line?
0. T is 0.
Let t equal 0. So a point on the line,
1, 3, 0.
point on our line is 1, 3, 0. And what's our direction vector? It is parallel, yes.
Thanks, Connor. Thank you. 1, -1, 2.
That's a coefficient on the parameter here. So our direction vector is going to be 1, -1, 2, that vector. I'll call this point P. This is on the line. I'll call this point Q. So vector PQ is going to be the vector 0, -2, 5. And our distance is going to be the magnitude of PQ cross V over the magnitude of V. Well, PQ cross V is I hat, J hat, K hat, 0, -2, 5, 1, -1, 2. We'll do that determinant. When I did this out, I get I hat plus 5j hat plus 2k hat. And the magnitude of that square root of 30. 1 plus 25 plus 4. The magnitude of v is the square root of 1, 2, 6. So our distance is going to be the square root of 30 divided by the square root of 6. So we get the square root of 5.
And then if we were providing this distance, would we also provide the direction that it's in by supplying vector q? It's like,
Well, the distance is always going to be the perpendicular distance from the line to the point.
okay, so it's a completely different
Right.
situation. Okay.
Right. So we go back to our diagram here. We're looking for that
exactly.
perpendicular distance.
It's not just like it's the shortest distance.
Right. The
from-
shortest distance. Distance. When we talk about distance, we always want the shortest distance. All right. Questions. When we come back, we will talk about planes in space. And in a lot of ways, planes are easier to work with than lines. Planes are a little nicer than lines. And we're going to talk about the distance from a point to a plane. And that's going to involve another nice vector quantity that we've been talking about.
Why do you need a note card for the physics test? It's not attainable. Like, these are
I'm pretty much gonna look through it, find pieces problem, do that, and stop.
All right, there you go.